Let's look now at what happens if we try and put a third substituent on the aromatic ring. We've already got two existing substituents on the aromatic ring. Now we're trying to see if we can add a third. And what we're interested in here is, again, the directing effects that each group is going to possess. So what we can do is, I'm just going to pretty much summarize what we've got up here. We've got an aromatic ring. We're going to add some sort of electrophile, which I'm calling Y plus, to that aromatic ring. And what I'm going to do is I'm going to try and figure out where the Y plus will be directed to. Now the nature of Y plus is really unimportant. All that matters is the nature of these groups that are on the ring. Now if this is activating, it means it's going to be pushing electrons into the ring, which means it will end up directing ortho and para. But since there's already a group down here in para, we really can't talk about that. So the activating group will be pretty much directing just ortho. Now this deactivating group here will direct meta. So what we're seeing here is the activating and deactivating groups are actually directing to the same carbon atoms. What this means is we expect to get just one product here, and that is the product where the Y connects to either of these ortho carbon atoms. Now since this is symmetric, it doesn't matter which one it connects to, it's going to be the same thing. Right, let me give you an example of that. An example would be this one here where you've got an activating group, that's the OME, that's going to be pushing electrons into the ring. And the reason we know that again is because we draw this out. We see a single bonded oxygen, it's got a delta minus, so we know that's going to be pushing electrons into the ring. The NO2 looks like this, and we know that that's going to be sucking electrons out of the ring because we've got a positive charge on the nitrogen in the nitro group. So I'm just going to show that. Alright, so this is pushing electrons in, this is sucking them out. Alright, let's look at the product we'll get from that then. And that will be this product. The HNO3 H2SO4 produces NO2 plus as the electrophile. So I will just throw the NO2 onto that position. Now because this is symmetric, the NO2 can either go here or here and it will be the same compound. So that's the only product we get if we have an activating and deactivating group para to each other. Alright, in the case of an activating and deactivating group in the ortho positions, we can look at the activating and we can say, well, that's going to direct here, be ortho, and it will also direct para. It would direct here, except there's already a deactivating group, so I'm not going to worry about that. In this instance, the deactivating group will direct meta to the deactivating group, so we're looking at this position here and this position here. So again, the activating and deactivating groups are directing to the same carbon atoms. So what we'd expect there are two products. This one would probably be the greater percentage of the two because we've already got a group here. We'll probably have some steric things going on where the activating group might get in the way a little bit, so we might get a little bit less of this one than we would expect. Alright, so here's an example. We've got an NH connected to an alkyl group. And we know that that's going to be activating because we have a lone pair on the nitrogen here, so it's going to be delta minus. And we know that that's going to be pushing electrons into the ring, so that's going to be an activating group. The other one is this, which means we've got a delta minus on the O and a delta plus on the C. So what's going to happen is that's going to be sucking electrons out of the ring. So we know that that one is going to be deactivating. So that's the situation we have. It's the same as what I had in the example. So the two products we're going to get, just going to make a bit more room here in a second. So we'll get two products. And one will be connected down here. And one will be connected over here. And if I want to know, if you want to know how I got the actual electrophile that's attacking there, what I do is I draw out the AlCl3, and I draw out this compound, and if it's got a COCl attached to it, then it's going to look like C double bond O and Cl. That's the only way I can draw it out, so that the carbon ends up having 4 bonds. So I put the Cl on the AlCl3, and this is what I've got left over, and the electrophile will be this, where the positive charge ends up on the C that had the Cl connected to it, as we would have predicted. That becomes negative, all of this becomes positive, where the positive charge ends up on that C. And of course the C positive is what joins onto the ring, and that's what we've tried to show here as well. Alright, so that's for the case where we've got an activating and a deactivating group in ortho positions on the aromatic ring. What if we've got two deactivating groups? Well, what's going to happen there is this deactivating group will direct meta, and this deactivating group will also direct meta. So we're actually going to end up with just the one product here, and the one product we end up getting in this instance would be this. Alright, I've already described why NO2 is deactivating. Let's look now at why CN is considered to be deactivating. Now if you look at CN, it's actually C triple bond to an N, which means that that's going to be delta minus, which means that the C connected to it will be delta plus. So we know that that's sucking electrons out of the ring. We already know that NO2 sucks electrons out of the ring because it's got a positive charge on the N. Let me show you how I get the group that's actually attaching to the ring. And that's going to be from looking at the reagents on the arrow. So again, I draw out my AlCl3 and my compound, showing the bond to the Cl. So I bond the Cl to the AlCl3. That's going to be negative, and whatever else is going to be positive, and the positive charge will end up on the C that the Cl was connected to. So our electrophile that we used there was going to be CH3, C plus, and then the CH3. So that's what's going to go on, and we know that the ring will join on to this positive C of the electrophile. and that's what we're seeing up here. And it only goes into this position that's meta to both deactivating groups.